Hello there, students. Welcome back to physics. We're going to talk about circuit analysis. It's kind of fun to do circuit analysis. It's kind of like, I think of it as a puzzle. It's like you're just looking at this puzzle and you're using the sort of rules that you know about circuits in order to solve the puzzle. But you have to know the rules first, and that's kind of what we have to go over first before you can start to solve the puzzles. Now, some of this should be reviewed from grade 9, so I'm just going to go through it quickly. So just watch this as a refresher from what you have learned in grade 9, and we're going to extend those rules and learn a couple new ones next week. But for now, let's just review the basic elements of electrical circuits. Okay, so this is a parallel circuit. There are 3 branches. Each of these represents a load, could be a light bulb or something like that. This is a battery over here. So electrons could travel down path A. They leave the terminal of the battery and they do this. They take a trip around the circuit. And they return back to the source. They could also take path B, in which case they would follow that path there on those arrows, or they could follow path C. And here is all possible paths. Now, some arrows here are incorrect. Take a moment, pause the video, and see if you can figure out which arrows are pointing the wrong way. There they are, and that's better. So this is the correct sort of arrow diagram of the circuit. A question to ask yourself is, where is the flow of electrons heaviest or lightest, or is it the same everywhere? Once again, just like take a moment, think about this for a second, see if you can answer the question in your head before I answer it. Pause it. And that's the answer. So over here, the flow is heaviest. It's not the same everywhere. Now, why is that the case? So let's take a look at where it's medium. So it's medium here and down here, and then it's lightest over here. So why is that the case? Well, all of the electrons start at the battery. And by the time they get over here to this junction, some of them go this way and some of them go this way. And so the flow sort of splits into 2 groups, and so it's going to get lighter there. But before it's even gotten to this junction, it hasn't been split up into groups, and so it's going to be heavier here. By the time it gets all the way over to the 3rd branch, you have a group that's already been split, and then you're splitting it again, so you're going to get an even lighter flow over on the 3rd branch by the time you get over to the 3rd branch. But you'll notice that the flow is equal on each of the 3 parallel branches because it's getting split off, so you get the same amount here and here and here. Now that depends on the actual loads. So what if the loads are not the same power? You could have a light bulb here and a blender there and a hairdryer there. And you can see that different loads require different amounts of power, and so you're not necessarily going to get exactly equal flows of electrons on each of the 3 parallel branches in a circuit. Okay, so let's go back to the basic idea of a parallel circuit with 3 branches. Let's say that there are 6 volts. That's the voltage of the battery. Now, think of voltage as sort of like money. You have a certain amount of, each electron has a certain amount of money, and it has to spend it all before it gets back to the battery. And then it's sort of like an allowance. The battery gives the electron an allowance of $6, and then the electron has to spend it somewhere along its journey before it comes back. So it spends, in this case, if the electron takes path A, it only has one place to spend its voltage, and that is at this load right here. So it spends all 6 of those volts right there at that load. If it takes path B, it's the same idea. It can only spend that voltage in one place right there. And same thing with path C. Now, let's say, for example, that these light bulbs have different resistance values. So 1 ohms, 2 ohms, and 4 ohms. But we already know by thinking of this voltage as this sort of like money idea that each electron has to spend 6 volts exactly at those loads. Well, you can calculate the current based on the voltage and the resistance. So the question is, what is the current at different parts of the circuit? Well, it's going to be different if you have different resistances at each light bulb. So at load 1, let's do that first. Given these voltage and resistance values, the formula, which this is from Ohm's law, which you learned in grade 9, the current is equal to the voltage divided by the resistance. So just divide those numbers and you should get 6 amps. Do the same calculation for load number 2, 3 amps. Same calculation for load number 3, 1.5 amps. So you get these different current values. You get a much higher current, which is the flow rate of the electricity, when you have a lower resistance, which makes sense. And just make a note of the fact that the current is the same up here as it is down below the load. So going through the light bulb doesn't change the current. Now, this is an important rule. This is a rule about the current flow at an intersection in a circuit. So let's focus on these intersection points here, 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 and here. And the law, which is known as Kirchhoff's current law, is that the total current coming into an intersection is equal to the total current going out of the intersection. And let's look at an example of how that works. So right here, we've already calculated that there are 3 amps on this branch and 1.5 amps on this branch. And each of those branches are coming out of this intersection right here. And so we know the total current going out of the intersection, which is 3 plus 1.5, so 4.5. And so therefore, the Kirchhoff's current law says that the current going into the intersection must be equal to the current going out of the intersection. And so therefore, this current right here, which is coming in, is equal to the total of these two, 4.5 amps. Same thing here, 4.5 and 6 going out, which in total is 10.5. So therefore, the current over here, which we didn't actually know already, is 10.5. And that means that the current at the battery is 10.5 amps. So we have now solved the current at the battery, which was not previously known. The current, so Kirchhoff's current law, which is about intersections, we can now make that more specific to types of circuits. So we could say Kirchhoff's current law for parallel circuits is you add all the currents up throughout the parallel branches. So on this branch, 1.5, so each of the 3 branches, we have 6, 3, and 1.5. If you add each of those up, you get 10.5, and that is equal to the current at the battery. And so that's what this expression means. The current of the whole series is equal to the sum of each of the currents in each of the branches in a parallel circuit. Now this is a series circuit. Kirchhoff's current law for that should say series, not parallel. Sorry, let me just change that quickly. For Kirchhoff's current law for series circuits is just that the current is equal at each load. So just take a look at this. It's 10.5 amps everywhere because there's nowhere that it's going to split into groups. It's just the same group of electrons going around at the same rate all throughout the circuit. And so that's what this law says. I of the series is equal to I1 equals I2 equals I3, and so on, as many loads as you have in a series circuit. Now there's another rule, and this is about voltage instead of current. Now I find voltage a little bit more confusing, a little bit harder to wrap your head around. This is the idea of think of money, think of allowance. You have to spend all your money, spend all your voltage by the time you get back to the battery. So Kirchhoff's voltage law is that the voltage which is given to an electron by the battery or the power source is equal to the total voltage spent by the electron as it travels through the circuit. Okay, so for example, if there's a battery here and at the battery each electron is given 16 volts, then it spends 8 of them here and it spends 3 of them here. So how much is it going to spend here? Well, you just subtract 16 minus 8 minus 3 is equal to 5. And so it has 5 volts left to spend because it already spent 8 here. It's down to 8. It spent 3 here. Now it's down to 5. So it must spend 5 here so that it perfectly spends everything by the time it gets back to the battery. So let's now make this, let's write the specific Kirchhoff law for the voltage of a series circuit. In a series circuit, you add up the voltages at each load in order to equal the total voltage of the series. Now this is a parallel circuit. The question is, what is the voltage of this electron? Or sorry, what is the voltage at this load? Oh, that's sort of a hanging slide. Oh, I put my summary in the wrong place. Let me just fix that quickly. That's why I'm confused there. And let's go back to that. So the question again was, what is the voltage at this load right here? Well, you can see how no matter which path the electron takes, whether it takes path A, path B, or path C, it's going to spend 5 volts along the parallel branch. But it started with 9 volts, and remember it needs to spend all of its volts. So it must spend 4 volts here. 9 minus 5 is 4. So each electron spends 4 volts here, and then takes one of these 3 paths and spends the rest of its 5 volts on its parallel branch, and so it's down to 0 by the time it comes back to the battery. So Kirchhoff's voltage law for parallel circuits is that the voltage is equal across multiple branches. Because if we look back at this example, if all of the electrons spend 4 volts here, now they're each going to only take one of these paths. So it must be true that no matter which path they take, they must spend the same amount of volts on that path, because they all must come down to 0. They must all spend all of their volts by the time they come back to the battery, so they have to spend the same amount no matter which path they take. So therefore the voltage across each parallel branch is equal according to this law. So in summary, now I believe all of this should be reviewed from grade 9, but it's 2 years since you've done it, so let's just take a moment to take a lesson to practice this and refresh your memory on this. This is Ohm's law. V is equal to IR. You can reformat it into a couple different formats depending what you're looking for. Kirchhoff's voltage laws, voltage is equal in parallel branches and additive in series. Current laws are opposite to that. Current is additive in parallel branches and equal in series, and that is it. So thank you very much for watching, and go try your homework.